Bam! Mr. True. In this lesson, we are going to take a very detailed, in-depth look at graphs of polar equations. If you're just looking for a little piece of information, I've got a whole bunch of links in the description of this lesson if you just want to jump ahead to maybe just look at graphing Rose curves, okay? But in this full-length lesson, we are going to be looking at identifying the three types of symmetry that we can expect to see in our graph by some kind of algebraic test to our equation. So there's three types of symmetries to test for. We are going to be looking at the special types of graphs. What is the polar graph going to look like just by looking at the equation? So can we, by looking at the equation, identify if it is going to be a circle, a lemniscate, a Rose curve, or finally a lemniscate, or a lemniscate. I always say that wrong. Lemniscate. And our last page here is just our examples being done. Okay, so first, by just looking at the equation, can we identify any symmetries that will be in the graph? That will save us some points. Maybe we can only plot, half the points, maybe instead of all of them. We'll notice as we're plotting, we're kind of getting a picture. We know there's going to be some kind of symmetry, and we can just stop earlier and kind of mirror it and be done a lot quicker, because these are going to be tedious graphs if you're doing them completely by hand. We'll use a little aid of a calculator. Symmetry for polar graphs, or of polar graphs. They can be symmetric to the polar axis, the horizontal axis. Don't call it the x-axis because we're not in a rectangular coordinate system. And of course, I'm assuming we've already talked about graphing just simple polar coordinates, where we rotate the pointer, if you will, and if after the rotation theta, if the radius is positive, we'll go towards the direction of the pointer, and if the radius is negative, then we'll go in the opposite direction of the pointer. So this is not just plotting individual coordinates. That's assumed to already be understood. And I'll have a link here if you're not sure how to graph polar coordinates. This is about the graphs. If you can replace theta with negative theta, or replace r theta with negative r pi minus theta, some textbooks include this extra check and some of them don't, and it's or. You don't have to do both. If that yields an equivalent equation, then your graph will be symmetric to the polar axis. And if you know that, you can maybe plot a few or less points and get your graph quicker. If your equation only involves cosine, then it will be symmetric to the polar axis. Now, by symmetry to a polar axis, that's symmetry to a line, so we're talking about a reflection. So if you have a point in quadrant 1, say here, then you can be guaranteed that if you reflect or sort of fold that graph over the polar axis, this line right here, then you will land on another point on the graph. Now, when you're graphing polar coordinates, you're allowed to have a negative radius, right? So if you, again, have that pointer starting off at 0 degrees radians, or 0 degrees, did I just say 0 degrees radians? 0 radians or 0 degrees. If you rotate that pointer in a direction which is opposite to where your point is. Now, opposite means that we're looking at a difference between this angle and this angle of some kind of, well, I guess you could talk about multiple rotations, but let's just say they're separated by basically 180 degrees or pi radians. Then you could just simply go backwards. Now, all these thetas that I'm drawing, remember too, these are all reference angles which are equal, the number of degrees or radians between the polar axis. And, well, if we were graphing angles, the terminal side of the angle. So if this were, say, pi over 6 radians, then it could be a reference angle over here of pi over 6 radians, or pi minus pi over 6, which would be 5 pi over 6 radians. And if you then could go backwards opposite, with that opposite radius value, that negative radius value, you could land on the same point as well. So that's where this r comma pi minus theta alternate substitution comes in for checking for if you have any symmetry to the polar axis. Now, on our first example here, and it's going to be the only real simple example of testing for symmetry until I get to the graphs and I'll kind of build it into those problems, we're going to check for symmetry for the equation r is equal to 3 plus 2 cosine theta. Well, I kind of already gave you a cheater note. I said if your polar equation only involves cosine, you will have symmetry to the polar axis, but assuming I didn't give you that little shortcut tip, other types of, you can have other polar equations be symmetric to the polar axis. Otherwise, if that's all there was, I wouldn't need to be teaching you some kind of check, right? Okay, so if we replace theta with negative theta and it simplifies to get back to the original equation, or take out r and replace it with negative r, and take out theta and replace it with pi minus theta, if that also simplifies to the original equation, or both checks don't have to pass, but if that one substitution worked, then we could be guaranteed to have symmetry to the polar axis. So I've taken out our theta and replaced it with negative theta, but the cosine of negative theta is the same as the cosine of theta because the cosine function is an even function. Hopefully you've already studied that in your trig class. Even functions, and you studied the definition of even functions even back in Algebra 2 and Pre-Calculus, where if you could plug in opposite numbers you get the same answer. The cosine of pi over 6 is square root of 3 over 2, and the cosine of negative pi over 6 is also square root of 3 over 2. So just by the fact that cosine is even, we're already back to our original equation, and thus we're guaranteed to have symmetry to the polar axis. Now if I take out r and replace it with negative r, and take out theta and replace it with pi minus theta, and then use the difference identity for cosine to expand and then start to simplify, the cosine of theta is negative 1 and the sine of, did I just say theta? I did. The cosine of pi is negative 1 and the sine of pi is, well, 0. You see here as we continue to simplify, we get r is equal, we have to divide everything by negative 1, we get r is equal to negative 3 plus 2 cosine of theta. And that does not look the same as this. And you have, again, those sort of special differences between plotting polar coordinates as opposed to rectangular coordinates, where one point in a polar system can have many different ways, an infinite number of ways, of getting to that one point, whereas in a rectangular system it's unique. So while this equation does not look the same as this, they actually do yield the same graph. Now of course you don't know that, we're just starting off. So I'm going to just say this. When you're testing for symmetry, if this is the only test that we did, the algebra would show that, well, not that there's no symmetry to the polar axis, but just that we're not guaranteed. So these three checks that I'm giving you for, oh, and by the way, we wouldn't have had to do both of these. As soon as we did one check and it worked, we could have stopped. If the algebra check fails, it's not that that symmetry, again, does not exist. We're just not guaranteed that it exists. You might still notice a symmetry as you develop your graph. It's just that you had to plot more points maybe to see that symmetry start to happen, as opposed to an algebraic check that just told you immediately, and thus could save you some time. Respect to the line of theta is equal to pi over 2. Well, that's, again, theta equals pi over 2. So hopefully in an earlier section you notice that, let's see, if I want to graph theta equals pi over 2, I don't care what the radius is. All I care is that every point on that graph has a rotation of pi over 2 radians, or 90 degrees. So if I start from 0 and I rotate pi over 2 radians, or if I rotate 90 degrees, and then I don't care what r is, then that's this line right here. Every single point on, let's see here, color I haven't used yet. Every single point on this line has a rotation of pi over 2 radians, or 90 degrees. But this equation, sort of weird that I'm giving you an equation of a polar graph in a section where we're introducing graphing. So let me just try to explain this. I don't care how far each of these points are. There's no value of r in this equation, just theta. They have to be a rotation of 90 degrees or pi over 2 radians. So we have a symmetry to this line. That means we have a reflection. Every point to the right, I guess you could say, is going to have a reflection to the left, or if you fold the graph on that line, they're going to line up and with another point on the graph. And that symmetry, that reflection over that line, theta is equal to, pi over 2, that can be identified ahead of time before you start actually making the graph, is if you replace r theta with r pi minus theta, or negative r negative theta. This is going to be the one that we use the most in our examples of this video. If you can plug those in and get simplify and get an equivalent equation, then you're guaranteed to have symmetry to the line. Theta is equal to pi over 2. Any graph that just involves, or any equation, polar equation that just involves sine will have symmetry to the line. Theta is equal to pi over 2. Okay, there is one more check for symmetry, and just before I get to the next board, again, I'm going to just say one more time, if any of these algebraic checks fail, you can still have that symmetry. You're just going to have to plot more points to see it in your graph. The third type of symmetry that we can check with algebraically, and we're going to be concerned with in this lesson, is the symmetry with respect to the pole. If you can replace r theta with r pi plus theta or negative r theta and get an equivalent equation, then you are guaranteed to have symmetry to the pole. Now, what does symmetry to the pole look like? Well, it looks like we have this point here in quadrant 1. It doesn't have to be in quadrant 1, but you know, if the graph is symmetric to the pole, then you can either look at it as two different ways. We can look at it as a reflection over the line, the polar axis, so we can reflect that point over the polar axis and get it down here, and then reflect it again over the line theta is equal to pi over 2, and see two reflections to get from the original point to another point which is symmetric to the pole. Or I always just say that it's a rotation of 180 degrees or pi radians around the pole. So if I take this graph, if I take any kind of graph and I rotate it pi radians about the pole, about the center, if it was a rectangular system around the origin, and the graph lines up on itself again, then you have that symmetry to the pole. And with this rotation idea, if we rotate, you know, some kind of radians, and let's say it's a reference angle, like, oh, I don't know, pi over 4 radians, then if I go over here at pi and I rotate the same reference angle of pi over 4 radians, keeping the r value the same, you would end up again with that pi radian rotation, or that another point where if you reflected about the line of the polar axis and about the line of theta is equal to pi over 2, you'd end up on that same point. Or you just keep the pointer going in the same direction, right? Your pointer indicating, of course, your angle of rotation that you do first, and then you plot the point. Well, instead of just stepping out a positive r units for the radius, you can just simply go in the opposite direction and have negative r theta. One more time, if any of these symmetry tests fail, you may still see the graph show one or more of these symmetries when you're done. The test again of these, the algebraic test of these symmetries, is if they pass, then you're guaranteed that type of symmetry, and that can save you, you can reduce the number of points you have to plot to finish your graph. Now, the special types of graphs. The first special type of graph are indicating, looking for the fact that it's going to be a circle. If you see r is equal to a, which can be any kind of constant, it could be 3, it could be 5, it could be negative 2, but some value of a, well, it could be a decimal as well, like negative 2.3, but if you have sub r is equal to some kind of coefficient, some kind of constant, times the cosine of theta. Now notice there's no b or c, there's no variable in front of theta with this general form in this equation. If it's specifically a times the cosine of theta, 1 theta, then you're looking at a circle. If you have some kind of like 2 theta, 3 theta situation going in there, well then it's not going to be a circle. It's going to be another type of polar graph that we're going to be talking about shortly. Now if it is r is equal to a cosine theta, then cosine being an even function, you're going to have that symmetry about the polar axis, and the distance from the diameter basically of the circle passing through, in this form, passing through the origin to the opposite side of the circle, that whole distance, the diameter, is going to be a. And if you have r is equal to a sine of 1 theta, then you have again a circle. So any kind of constant coefficient of 1 on theta, all you have going on there is sine. There's no like plus 2 or something, or not, there's no plus 1 or something like that. That's going to be some other type of graph. It's just a times the sine of theta, then you're going to be looking for looking at a circle, again passing through the pole. I think I said pole instead of the origin, origin instead of pole over here, but it is passing through the pole. It is going to be symmetric. Because the sine function is odd, it's going to be symmetric to the line theta is equal to pi over 2, and again, that entire diameter is going to be a. By the way, and this will become really nice when we are graphing the roses, or examples there, but to solve for the maximum value of r, the maximum distance, any point on your graph is going to be away from the pole. To solve for that maximum absolute value of r, remember that the sine of b theta, now we don't have b here, okay, this is just in general terms of the whole lesson, the sine of some kind of angle measure and the cosine of some kind of angle measure, well, sine and cosine is that wave, right? It goes down to a minimum value of -1 and a positive value of +1. So the range of sine and cosine is only between -1 and 1. And then ultimately, if there's some kind of coefficient out front, of course, it's going to increase that value. Like if this was 3 cosine of theta, well, then the farthest distance away from the pole is going to be 3 units away, because 1 times 3 is equal to 3. And if it was -1, well, we have the absolute value wrapped around the r. Okay, now the next type of graph that we're going to be taking a look at, and we are going to do an example of graphing, this special type is a lemmaison. After circles, our second form of polar graphs are lemmaison. They are going to be symmetric to the polar axis when they're in the form of r is equal to a plus or minus b cosine of theta, and symmetric to the line theta is equal to pi over 2 if they're in the form of r is equal to a plus or minus b sine of theta. Now, these are, if an equation is exactly in this form, it can't deviate. A and b can be pretty much any value, but we have coefficients of 1 on the theta in the functions of cosine and sine. So that's how you recognize if the equation looks like this, it is going to be a lemmaison. And there's 4 different types of lemmaisons as well. Even though I'm telling you this is going to be symmetric to the polar axis and this is symmetric to the line theta is equal to pi over 2, when we get to this example, we are going to do one of these examples. I am going to go through those 3 symmetry checks that I showed you at the beginning of the lesson. Now, if you take the constant of a and you divide it by the coefficient of b, and you get a value which is less than 1, then you are going to be looking at a lemmaison which has an inner loop. And our example is going to be a lemmaison with an inner loop that we'll be doing after this. If you take a and divide it by b, and you get a ratio which is equal to 1, then you're going to be looking at a lemmaison which is specifically a cardioid, which kind of comes to a point, if you will. The inner loop sort of starts, I guess, but it fails to finish. You have a little point, a little sharp bend there at the pole. Now, you just simply have a dimple, as you can see here, if a divided by b is greater than 1 and less than 2, and if you take a divided by b and you get a value which is greater than 2, then your lemmaison is going to be identified as being convex. There's no place where it caves in, if you will, so it's convex instead of concave. Now, up here, I kind of ran out of room when I started to draw my first polar grid. You definitely want to go to the internet. I'll put a link right here of some website that you can go and print a piece of paper with probably about 6 polar grids on them, because you don't want to make them from scratch every time like I am doing. And I'm identifying the angles here are really the angles about the unit circle. Now, you don't have to use the angle measures around the unit circle to make a polar graph. Indeed, when we get to roses, when there's a lot of petals, if you were to make those by plotting points, you would want to make your increments much smaller than they are on the unit circle. But there's not a tremendous amount of crazy movement going on with these 4 types of lemmaisons. So when you do these particular graphs, when you make the table of values, you can do them by hand and maybe count every, well, if you're doing them by hand, you can just put the angles that are from the unit circle into your table. Or and I'll be showing you in the sort of a pop-up window in our video lesson that you can put your calculator, you can use the table command or the table feature in your calculator and set it up to work with increments of 15 degrees or what would that be, pi over 12 radians. And then you can just skip some of these because this is going to go, if this is the unit circle, from here to here is pi over 6, which is 30 degrees. And then you get to pi over 4 or 45 degrees and it starts to count by 15. That's why you want to set your calculator, your table, to go by 15s or by pi over 12 because that's going to hit all the values around the unit circle. So let's get to that first example right now. Example number 1, r is equal to 1 minus 3 cosine theta. Test for symmetry. Well, is it symmetric to the polar axis? Well, can I plug in r negative theta in place of r positive theta, really just substituting theta for negative theta? If I do that, we are going to get r is equal to 1 minus cosine, 3 cosine of negative theta, and because again cosine is an even function, we get 1 minus 3 cosine theta. So yes, we plugged in negative theta and we got right back to where we started from, so it is going to be symmetric to the polar axis. Is it going to be symmetric to the line theta is equal to pi over 2? Well then, in that case, I have to replace r and theta with negative r, negative theta. Well, again, the even nature of cosine is going to allow that negative theta to just be canceled out and keep it as negative 3 or minus 3 cosine theta, but there's no way to get rid of the negative r and simplify it back to what it was in the first place. So that doesn't mean this is not going to have symmetry to the line of theta equals pi over 2. We just aren't positive. And you can already see here, if I let r become negative theta, or excuse me, if I replace that with negative r, there's no way that's going to cancel that out either and get us right back to where we started from. So we're guaranteed with our 3 algebraic checks that we're going to have symmetry to the polar axis. As far as the line, again, theta is equal to pi over 2 and the pole, it may have symmetry to those items, and it may not. We're not sure. If it just happens to show up in the graph, then, you know, all the better. What is the maximum radius? Well, again, that sine, because now you might be looking at these problems and they might have other trig functions besides sine and cosine. Most of these that we deal with in this lesson will. So the maximum cosine is ever going to be is positive 1. Well, 1 minus 3 times positive 1 is 1 minus 3, which is negative 2. And the smallest value that cosine of theta can take on as an answer is negative 1. So 1 minus 3 times negative 1 is going to be 1 plus 3, which is positive 4. So the maximum the radius is ever going to be, or the maximum value, again for the absolute value of r, is going to be 4. And at what values or measurements of theta is that maximum value of r going to occur? This particular step is really convenient when you're graphing roses, but let's go ahead and do it now for the limacon. So we're going to have 4 is equal to 1 minus 3 cosine theta. We're going to subtract both sides by 1 and get 3 is equal to negative 3 cosine theta. Divide both sides by negative 1, or excuse me, I'm thinking of the answer, by negative 3, and get negative 1 is equal to the cosine of theta. And now, you know, to get that theta out of the cosine function, we need to take the inverse cosine of both sides of the equation. I'm also going to flip this around. So we have theta is equal to the inverse cosine of negative 1. And if you know your unit circle, you don't need a calculator for that. What angle measure in radians is going to give you a cosine value of negative 1? And of course, cosine of theta is equal to x over r. Well, that's going to be pi. So on that graph over here, we're guaranteed, or we just simply know at this point, that we're going to have a point of, well, 4 pi. So if this, of course, is 0 degrees radians, pi over 2 radians, and finally pi radians, when we rotate pi radians and then step out 4 units, that is going to give you a point right here. So at least we know one point now that makes up our polar graph. Now to complete the table, I don't think your well, it depends on your teacher. Again, we can put these into just a unit circle type thing, and why am I stopping this table at pi? Well, it is symmetric to the polar axis. So if I work through a rotation of 0 to pi, then I think I'm going to have a nice set of points that I can reflect over the polar axis and finish my graph. So I think that's all we're going to have to do. So at 0, well, the cosine of 0 is 1. And of course, that's going to be 1 minus 3 times 1, which is negative 2. And then we can put in pi over 6. The cosine of pi over 6 is square root of 3 over 2. And square root of 3 over 2 times 3 and then subtracted from 1 right off the top of my head is going to be approximately equal to negative 1.6. Now, plugging in pi over 4, the cosine of pi over 4 is the square root of 2 over 2. Multiply that by 3 and then subtract that product from 1, and you're going to get approximately negative 1.12. Now, I'm not putting my answers in exact format because that's going to be quite difficult for just plotting on a polar grid. And this is, well, I'm calling this as a graph, and we're going to have quite a few points to make it up. I don't want to be graphing, I don't know, 5 square root of 3 over 2. Where exactly is that? So I'm getting decimal approximations. And that means that, I really can just use a calculator to get these values. So let me show you how that looks on a TI Nspire. So you'd like to graph a polar equation with your graphing calculator. Well, this is what it's going to look like on a TI Nspire, whether it's CAS or not. We're going to toggle between the scratch pad and go to the calculator. Nope, don't want the calculator. We're going to the graphing calculator portion. We're going to hit Menu. We're going to go down and select 3 for Graph and Edit Entry, and that's where you can tell it that I want to graph a polar equation. So we're going to be graphing in this a lemma with an inner loop, and that equation is going to be 1 minus 3 times. And sometimes you can get away with not hitting that times button and just let it be assumed to be multiplication, but then other times the calculator doesn't like that. So 1 minus 3 cosine of theta. Where you're going to go for theta, one place is to come down here where the pi symbol is, open up that window, arrow over to theta, select it, and of course, well, that is what we want to graph, 1 minus 3 cosine of theta. You can change the step of the graph here if you find that this is necessary. You can decrease the interval that theta is going to graph in, like say some graphs you can get away with, like if you're doing a rose with an odd number of petals, you could get away with this only going from 0 to 3.14, excuse me. And then some of the more complicated polar graphs, you actually want to extend that beyond 6.28 to get the entire graph. But this is going to be good for what we're dealing with. We're going to go ahead and hit Enter. And there is our lemma with an inner loop. But this calculator tutorial is actually part of a full-length lesson graphing polar equations. And we were interested in getting the values off of the table. So we're going to hit Menu. We're going to go down to Table. And I could have just hit 7. We're going to do it in a split screen, like right here. I'm going to hit the 1. Now, I have a table already set up, but I wanted to count by specifically pi over 12 radians, or effectively 15 degrees. So I'm going to go to Menu, I'm going to go to Table, we're going to edit it, the table setting. We're going to start that at 0, just for convenience. And we're going to count, I want to count by, again, pi over 12. So pi, Enter, divide that by 12. And now we have the table of values starting at 0. And at 0 radians, we had a radius of -2. At pi over 12 radians, we had a radius of approximately -1.9. At 2 pi over 12, or pi over 6 radians, we have a radius of -1.6 approximately. At 3 pi over 12, or pi over 4, we have a radius of -1.12 approximately, and so on, counting down by increments of pi over 12 or every 15 degrees. Now, If once you're done getting the information off this table that you like, you can turn it off. Now, if you select the graph portion of your split screen and you hit Menu, you might find it quite difficult to figure out how to get rid of that table. But if you select the table portion of your split screen, hit Menu, go down to Table, and you can remove it. And that is how you graph a polar equation with your Inspire calculator and create or look at that table of values if you need it. Now back to our full-length lesson, or if this is just the tutorial, the short tutorial you watched, thank you for watching. Okay, so as you saw from that demonstration of use of at least a TI Inspire, you might have noticed that I kind of made the graph to create the table. But just to make sure that we're comfortable plotting points, let's just walk through a couple of these. We have a rotation of 0 and a radius measure of -2. So with my pointer, if you will, again, when we plot points, I like to think of it as a pointer, again, on the pole. You rotate that first and then you move. Well, the pointer is pointing to 0, and then we move back 2 units because the radius is -2. And then we rotate that pointer to pi over 6 and move back approximately, somewhere between -1.6 approximately. So, I don't know, somewhere around here. Then at pi over 4, so our pointer is looking at pi over 4, we go back 1.1 units, so obviously that's going to be a little bit more than -1. Pi over 3, that's -1/2, so pi over 3, -1/2. I almost hit the wrong line there. At pi over 2, we have a radius of 1, so at pi over 2, we step out a length of 1. At 2 pi over 3, we have a positive radius of 2.5, so at 2 pi over 3, we go out 2.5 units. At 3 pi over 4, we go out to just past 3. So 1, 2, 3, just past that. And at, finally, where are we at? At 5 pi over 6, we're a little bit past 3.5. So somewhere around there. And then at pi, we're at 4. So if we look, and that's where you had that. So if you look at what we have plotted so far, 0 radians at -2, and then wrapping around, we have half of our cardioid, half of our lemmaison, from just going between 0 and pi. And now remember, we had that relation, that symmetry to the polar axis. So I'm going to grab another color just to show you the reflection. And let's see here. That point reflected over the polar axis here would be, again, just past 3.5, and then we were just past 3. And this reflected down is somewhere in the middle at, what was that? Oh, I lost my place here. Let's see. How about, oh yes, at 2 pi over 3, we were at 2 pi over 3, we're at 2.5. So reflecting that down to 2.5 radiuses length over the polar axis. And 3 pi, well, it's actually easier instead of looking at the numbers. Let me just keep the pattern up going here. So that's reflected, this is reflected down, this is reflected down, this is reflected down. Here we had at pi over 2, we were at 1, so we're going to reflect that down to be, match this radius of 1 reflected over the polar axis. This is going to reflect over, just to be itself, this is going to reflect up now. And this point's going to reflect up and up. Try not to lose your track here. And that is the other half of your cardioid. So that is the end of our first example. Let's move on to a different type of polar graph, which is called roses. Ah, yes, the rose curves, one of the prettiest curves you will make when making your polar graphs. They're going to be in the... Aren't you glad I was wearing a t-shirt that said I was right 98% of the time and wrong, or who cares about the other 3%? Well, this is one of those 3%. I made a couple of minor corrections through our lesson so far, but a nice student/viewer pointed out to me that my labels on my 3-petal curves in this introduction scene to graphing rose curves were flip-flopped. And, well, that's kind of a big mistake that's just sort of graphically screaming at you on the screen. So let's take take 2 of this introduction to rose curves and see if we can't do a better job. So the rose curves, again, r is equal to a sine of n theta, and r is equal to a cosine of n theta. Both the sine and cosine functions make rose curves. And it's the first general form you're looking at where we're able to have a coefficient in front of theta other than just 1. And a cannot equal 0 because a is going to be the overall sort of maximum length of these petals, and if a was 0, you would be just out looking at a point, or rose with petals of 0 length. Okay, so if n is an even number, then there are 2 n petals, and if n is odd, there are an n number of petals. And the maximum radius that your polar graph is going to take on is going to be the absolute value of a. And this is where the mistake was, some simple examples of what these are going to look like, and we're going to do 2 real examples with all nice, points and table of values and whatnot, would be r is equal to a cosine of 2 theta. That coefficient of n is even, so you're going to have twice the number of petals. Or r is equal to a cosine of 3 theta, and it might look something like this, where we have r is equal to a sine of 4 theta, giving us 8 petals, and another 3-petal rose based off of sine. I just didn't want to try and draw a 5-petal rose. Now, one thing to just reiterate one more time in our lesson, that if you have a polar equation only involving the cosine function, it is going to be symmetric to the poles. So if you see, if I fold this over the pole, well, the top half of this graph, if drawn accurately, was going to perfectly line up with the bottom half. With these even numbers of petals, you've got a lot more symmetry going on, but it's really nice with the odd number of petals to make sure, that your sketch is actually kind of coming out correctly. And sine has symmetry to the line theta is equal to pi over 2. So reflecting that over that line, theta is equal to pi over 2, you can see the graph line up on itself, and that symmetry is actually, thankfully, sometimes I don't know, make careless mistakes. I try and catch them all, but that was what allowed the viewer to catch on to the fact that I had made a mistake in my lesson. So thank you. Set the equation equal to a maximum r if n is odd, or r and negative r if n is even, to solve for theta to find the location of the petals. See, there is a lot of motion in these graphs. Look how much the radius is changing as I go around just this simple 3-petal rose. All of that movement, all of that change that we're seeing with the radius as we rotate around with theta means that if you're just going to plot these rose curves with a table of values, you're going to need a lot of points. So hopefully, we can set up our sort of formulas or equations here and find out theta, find the angles at which we can just go out that maximum r value and place the endpoints of these petals to get a rough sketch of what the rose curve is going to look like. And then if you want to add a few more points, you can. Okay, I was running out of room, so this is in purple. We're really going to start up here. To make a really accurate plot, if you need more than just the endpoints of these petals or if you're required to do more than that, you want to start with n theta to start building your t-table. And so n theta, you can see I'm just pulling values or angles off of the unit circle, so 0, pi over 6, pi over 4, and so on. Make that list, and then go through and divide them all by n. And so if n is just a simple 2, but I put it down, but that gave you 4 petals, a lot of movements with that. So we'd have like an angle of 0, an angle of pi over 12, an angle of pi over 8, an angle of pi over 6, an angle of pi over 4. I mean, that's kind of not, that's a lot of angles to only go pi over 4 radians. So you can see how long that list, that t-table would need to be to plot some points to get a good, really accurate graph of your polar equation. So again, hopefully we can just highlight the endpoints of those petals to get our sketch. Okay, and as you make this list of theta, so I lost track of what I was going to say, you would have to let theta, you'd need to let theta go from greater than or equal to 0 up to pi if n is odd, and to take care of the double the number of petals that you get when n is even, you would need to let theta go from greater than or equal to 0 and less than 2 pi if n is even, to get, again, all those petals. So now we got our correction done. Let's get back to our regular scheduled program. Bam! So from our algebraic tests of plugging in negative theta, negative r, and negative theta, and finally negative r, we know that this graph is going to be symmetric about the line theta is equal to pi over 2. That may allow us to, if we were doing a t-table, to do this graph, to maybe stop the t-table a little bit short or just do it in pieces so we can get the entire picture of the graph. But we're going to focus on just finding the endpoints of the petals. And it failed the symmetry of the polar axis and the pole. But again, that doesn't mean it's not going to be symmetric. It just means we're not guaranteed for that to occur. Okay, now each of these petals are going to have a maximum length of 4. So we're going to just identify the tips of these petals again. So we're going to set 4 equal to this equation. We're going to divide by 4. And now we're going to get that sine function away from the 4 theta by doing the inverse sine function. A little bit of review of solving trig equations. And now we're going to just start going through this. Now we're going to keep going, looking for values, angles that give us sine values of 1. And where do we stop? Well, because this n is even, we need our final answer of theta to go from 0 to 2 pi to make sure that we get the endpoints of all 8 of those petals. So let's see here. We're going to do 4 theta, and we're going to, let's see here, inverse sine of 1. So where does sine equal to 1? Well, that's going to be pi over 2. And let's see, pi over 2, 2 pi over 2, 3, 4, 5 pi over 2, 5, 6, 7, 8, 9 pi over 2. I hope you realize I'm just trying to move my arm around the unit circle to give you a visual. Where are we at? 9 pi over 2, 9, 10, 11, 12, 13. And then finally 13, 14, 15, 16, 17. Now I'm showing you the hand movements just to give you a visual, but I am just, adding the numerator here by 4 over and over again. There's a pattern to it, of course. We are just cycling around a unit circle. Okay, and that list keeps going, but do I need more to that list, or do I need to stop there? So we're going to now divide everything by 4, and we get theta. Again, we're dividing by 4 or multiplying by 1 over 4. So 1 over 2 times 1 over 4 is going to be 1 over 8. So we have pi over 8 and 5 pi over 8, 9 pi over 8, 13 pi over 8. Now if I were to extend that one more, you can see my numerator is just getting greater by 1. My next point would be 21 pi over 8. Well, 21 divided by 8 is bigger than 2. So we're moved past, beyond the 2 pi that we need. And also, if you take, let's see here, if you take 17 pi over 8 and you subtract 2 pi, you're going to realize that actually we can get rid of that as well, because 17 pi over 8, not only, actually, I really went too far, because 17 divided by 8 is also bigger than 2, so I really went way too far. If I take 17, so not only that, again, is also, sorry about that, bigger than 2 pi, but if I take 17 pi over 8 and I subtract 2 pi, right? I'm looking for a coterminal angle. Coterminal angles are angles that are separated by 360 degrees or 2 pi. So if I take this and let's see here, find a common denominator, that's going to be oh my God, chalk down! 17 pi over 8 minus 16 pi over 8. We're back to pi over 8. So not only is 17 pi over 8 bigger than 2 pi, so we don't need one that big, we don't need to go beyond 2 pi, but it's also coterminal to pi over 8, so it's in effect kind of a repeat angle. Well, now our n value here is even, so to find the endpoints of our petals, n is even. That means you have twice as many petals. That means we have 8 petals, not 4. But I only have basically 4 angle measures where we have a maximum value of 4. Well, that's because we need to set this equation equal to positive 4 and solve, which you just did. And we also need to set it equal to negative 4 and repeat. So I'm just going to step off, reveal that solution. Maybe you want to pause it, just practice it on your own, and then sort of clean all this up and get ready to actually draw the graph on the polar grid. So my 8 endpoints are 4 pi over 8, 4 5 pi over 8, 4 9 pi over 8, 4 13 pi over 8, and then with setting that equation equal to this equation equal to negative 4, we have the other angles of 3 pi over 8, 7 pi over 8, 11 pi over 8, and 15 pi over 8. Now if you look at the staggered, pi over 8, 3 pi over 8, 5 pi over 8, 7 pi over 8. It's going every 2 pi over 8. I have a maximum value every 2 pi over 8. Well, 2 over 8 reduces to 1/4, right? And pi over 4 means that for every 45 degrees, we're getting sort of the end of one of those petals. Now, the first petal is at 4 pi over 8. Now, this is marked off as a standard unit circle. Maybe you have some graph paper that includes basically a line at every 15 degrees. But let's see here. Pi over 8 is half of pi over 4. So pi over 8 is really 22.5 degrees. So we have, I'm just going to try and eyeball this. If this is 45 degrees and, this is drawn as accurately as I can sketch it, there is an endpoint there, and then every 45 degrees. So there and about there. Somewhere around here. Yes, okay. So we have pi over 8, positive 4. So we go from 0 to 4 pi over 8. And then, let's see here. How about it's going to look something like this. Okay, if I keep doing that, I'm just going to mess it up. Now, at 3 pi over 8, here, we're actually at negative 4. So it's like we're swinging out to 0. We went out to that positive 4. We came back to 0. And then at 3 pi over 8, which is, that line, if that's 1 pi over 8, that's 3 pi over 8, because we're counting every 2, which is back here. Then we're going to look something like this. Only we're cycling around this way, right? And then at 5 pi over 8, which is here, I believe, 1, 3, 5, yes. Then we're back to positive 4. And then at 7 pi over 8, which is here, we're at negative 4. And that's the 45 degree mark there. I'm trying to draw this as best I can. And then at 9 pi over 8, which would be here, we're back to positive 4. Whoops. 11 pi over 8, that's at negative 4. And 11 pi over 8 would be here, but that's at negative 4. Hope all my petals are coming out to be sort of the same size. And just keeping this pattern on, I'm going to swing this around. I just heard the static in the mic. I'm sorry about that. Where's my 45 degree mark? There it is. Okay, and that is the best I can do to sketch an 8-petal rose with just identifying where the end of each of those petals are supposed to be. So, and you know, that's a pretty darn good sketch. You know, I don't think you really need to make a whole bazillion, you know, a list of a bazillion points to find out exactly, like, is it there, or is it there, is that point supposed to be there, 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 you know. I know where the endpoints are. They all look pretty equal, and that is our sketch of an 8-petal rose. Now I was going to do another example where n was, sorry for the break. I was going to, I'm cutting the part of this lesson out where I said I was going to skip the next example where we had a negative a value and an odd value of n just because of the length of the lesson. Now, and then I thought, okay, I've got the example prepped. I'm just going to reveal the example, reveal the solution one step at a time, and really just give you the opportunity to pause the lesson and try it on your own. I'm not going to go over it because the process is just like this one, but you'll see the next example, see the solution revealed. Again, pause the video, try it on your own if you'd like. I think it's a good idea to make sure you get the process down. And then we will move on to the next type of polar graph. Bang! Alrighty then. So I said that I was just going to reveal this solution and not even talk about it because it was so similar to the previous example. But I realized as I was working this out, and you'll see that I added a little bit of extra information about plotting points with a table, that I think, you know, oh, the sun is out in different shirt, right? It's a different day. And I think I might have misspoke a little bit in the previous screen of, or scene of this lesson. And that rule was when creating tables, to simply make a, you know, plot a bunch of points to help you graph this rose curve, that I said let theta be between 0 and pi if n is odd, and let theta be between 0 and 2 pi if n is even. And that was a true statement, but I think I kind of emphasized that a little bit as I was setting up the equation to find the theta measures where the radius was at its maximum value, and that was incorrect. You do want to let, when setting up an equation to sort of locate the petals, you want to solve out for theta until you get to 2 pi. So 5 pi over 3 is the smallest answer that's less than 2 pi. Continuing that pattern on, we got 7 pi over 3 as our next answer, but that's bigger than 2 pi. And when you subtract 2 pi from this answer, you get back to pi over 3. So these three angle measures are where you're going to, again, find those maximum radiuses of 2, or the endpoints of those, what, 3 petals. Okay, so, but what I've done here is I have made a table of values to sort of plot the rows out with a, you know, a bunch of points. And you'll see that after we get past pi, the points start to repeat. So at 0 radians, we're at -2. At pi over 6 radians, we are at 0 already. At pi over 4, we're at 1.4. At pi over 3 radians, we have a radius of 2. At pi over 2 radians, we have a radius of 0. At 2 pi over 3, we have a radius of -2. At 3 pi over 4, we have a radius of -1.4. At 5 pi over 6, we have a radius of 0 again. At pi, we're at 2. Well, I've already got that point plotted. At 7 pi over 6, we're back at 0, but we hit 0 radiuses a lot, so don't worry about that. 5 pi over 4, we have a radius of -1.4, but I already got that point plotted. At 4 pi over 3, we have a radius of -2. So you see, after the table of values has passed that theta measure of pi, the points start to repeat. Now I also did not change the interval at which I was going to count these theta measures like I gave you as a tip in the previous screen as well, and you'll notice that I don't have very many points. I just wanted to show you that that could be an issue when trying to make a big table of values to plot Rose curves. So this is an increment of pi over 6 radians, and then we go to an increment of pi over 12 radians, and another increment of pi over 12 radians, and another increment of pi over 6 radians, or 30 degrees, 15 degrees, 15 degrees, and then 30 degrees. So I went back through the table of my calculator, and I started back at 0, and I filled in some of those points that I'd skipped, and basically just counted by every 15 degrees or pi over 12 radians. Now to connect the dots in order that they come out of this table, we get a Rose curve that looks like something like this, I hope. And then they start to repeat. So that is our 3-petal rose for r is equal to -2 cosine of 3 theta. Now we're moving on to, see if I can say this right, lemniscates. And the last special type of graph in these polar graphs that we're going to be taking a look at is something called the lemniscate. They're going to be in the forms of r squared is equal to a squared times the sine of 2 theta, and r squared is equal to a squared times the cosine of 2 theta, where a, of course, is not equal to 0 because then our petals, well, they would have no length. Okay, now in these forms, these are the only general forms that we have set equal to r squared. So they're going to be pretty easy to recognize, and if it's not set equal to r squared, then, well, I guess you could write it as r plus or minus, and then have a square root over the whole right-hand side of the equation. And these lemniscates that have sine values in them, they're only going to have symmetry to the pole. Whereas if you have cosine, they're going to be symmetric to the polar axis, that horizontal axis. The line theta is equal to pi over 2, again that vertical one, and finally symmetry to the pole. All right. Now our last example, I'm not going to include an example like this special type of graph. I want my last example for a lesson to be a non-sort of special type shape that you can memorize and just sort of know what it looks like before we even start. So we're going to be checking for symmetry in graphing. R times the sine of theta equals 4. Now, to put this into like r in terms of theta, of course, you're going to need to divide both sides by sine. So we're going to really just graph r is equal to 4 over sine theta. And this would be a nice format for your equation to be written in, especially if your graphing calculator only has a sine, cosine, or tangent button. But if you're able to directly enter cosecant, you might want to write that as 4 times the cosecant of theta. Now the process of this is going to be just like all the other 3 examples we've done in the lesson, where check for symmetry, build up a table of values if needed, because there's no petals here, I can't just find the endpoints of the petals, and then finally plot the points on a polar grid. Polar graphs can be very unique and very cool looking, very interesting, and have a lot of movement. The roses have the most movement, so I think if you do this in increments of pi over 12 or every 15 degrees, if you're doing it in degrees, radians are generally better, you're probably going to get a decent picture of what the graph looks like. So let's see. I'm going to reveal the solution one step at a time, so if you want to pause the lesson, try it on your own first. Last example, make sure you get the process down, and then I'll come back and talk about any issues that maybe we have and finish up or close the lesson. All right, well, we have, let's see here, r is equal to 4 cosecant of theta, and since cosecant is based off of sine, sine's an odd function, so thus our cosecant function is going to be odd as well. What does that mean? When we check for symmetry to the pole, we replace theta with negative theta. That means that r is now equal to -4 cosecant of theta, because with odd functions, if you plug in opposite numbers, you get out opposite answers. So symmetry of the pole is inconclusive. But when we replace r and theta with negative r and negative theta, everything simplifies back to the original function. So we are guaranteed to be have symmetry to the line of theta is equal to pi over 2. And by replacing r with negative r, our symmetry test for symmetry to the pole, again, it did not fail, but it is inconclusive. So we drew our polar grid. We went from 0 to 3 pi over 4, just working along with our calculator or the table function of our calculator to create these values. And we see that r is equal to 4 over the sine of theta is undefined at 0 degree radians. It'll be undefined at pi as well. And as we continued through our table of values and plotting the points as we went, well, they're just forming a straight line. So that is the end of our last example. I'm Mr. Tarrou. Go do your homework.